This is a look at Dr. Manthi's Orbital Viewer program, which runs under DOS, but it'll also run under Windows. Some systems do not support it well. This video may also serve as a basic introduction to what the pictures of atomic orbitals that you see in textbooks really mean. You can find the program by typing Orbital Viewer into your search engine and downloading. Here I have Orbital Viewer running, and you can see that this looks a lot like a 2p orbital. I'll show you the display. If you click on Display, you can see a number of options. We're not going to look at all of them. In fact, we're going to look at just a few. Today we click on Orbitals and we see we're working with one atom, and we're working on the second energy level. N is 2. For L, he doesn't have the quantum numbers, he just has the type of orbital, in this case a p orbital. And we've just chosen, of the 3 possible magnetic quantum numbers, we've chosen -1. Now what he's done is he's plugged these numbers into the Schrödinger equation, and he has solved it and given us a 3-dimensional rendering. Here we've used points to show the rendering. Now, the 3p orbital that we're working here, well, actually this is a 2p orbital. You can also see the asymptotes. You can see the node. It's a planar node between the 2 lobes of the p orbital. Here you can see that in some areas, right out here and right out here, the probability of finding the electron is very small. He has solved the Schrödinger equation. Each one of these points has a probability of finding the electron, but out here the probability is small, so the density is small. Here the probability is larger, so the density is larger. You see a lot more points. What are the 2 colors? The Schrödinger equation is not what he's graphing. The psi function is the basis of what he's graphing, however. The psi function can have a positive or a negative value. One side is positive and the other side is negative. And in the middle, there is a 0 probability. That's what that asymptote or node is showing you. We can turn this around and we can also see that this is a symmetrical probability around the axis that stretches this way. Let's now change to the display, and instead of showing points, which really is a more accurate way of looking at it, we're going to choose to display equal probability surfaces. And here what we do that is we put a polygon instead of the points. So when we click on this, we're going to see equal probability surfaces instead of the points, which are more 3-dimensional. And as you can see, we still have underlying the same probabilities, but the computer program has chosen a single probability and says, now, what is this in terms of a spatial rendering? How can we show equal probabilities? Well, it's a surface. So the probability finding the electron here and on the surface of this lobe here and here are all the same. So underlying again, you see the points, and the points are 3-dimensional of all probabilities, but here you have a surface of very small probability, and of course 0 probability in the middle. This is what we need to understand. If we change the display and go back to points, we see a more accurate picture, what I call a mosquito graph, of where the electron is. If we change the orbitals to the 2s orbital, we can see now a spherical distribution around the nucleus. We can also see that white area is a sphere, which is an asymptote, where the probability on the second energy level of finding the electron, there is a spherical node at that distance around the nucleus. We will now change again the display options to have polygons. So now we're going to get equal probability surfaces. And as you can see, whatever probability the program has chosen, that probability is the same all around. But inside this blue sphere, you see the points being rendered here for this 2s orbital. I'm going to do one more thing. I'm going to display a cutaway, if it'll allow me to do so. And we're going to pass a plane through the sphere. And you can see now, as we move this around, you can see more easily the spherical distribution of equal probabilities. He's done some shading here. And then you can also see that asymptote in the middle. If we move back to the point renderings, simply by clicking and moving it around, you can see that those points are still all there, but there's an equal probability surface around it. If we switch now back to points all around, and if we get rid of the cutaway, you can see the original probability coming back to us, and you can see the points in the middle. This is what we need to understand. The renderings that you see inside a lot of these textbooks don't look like this. They look like hard spheres. The electron is not taking a particular path around the nucleus. We cannot position it because of the uncertainty principle. The mosquito graph that you see here is a lot better rendering of the probability of finding the electron in the vicinity of the nucleus, because, as you can see in other places, the electron is acting like a wave, a standing wave, in the vicinity of the nucleus.